Okay, so here are the walkthrough solutions to the level 5 uncertainties problems. These are still looking at combining uncertainties, but the difference with level 5 is now we're looking at using two methods at once. So combining uncertainties where we've got two uncertainties for two quantities measured in the same unit, as well as combining uncertainties when we've got different quantities measured in different units. So these are the 5 examples from level 5. So, as you can see with question number 1, what you're looking for here is rate of temperature increase. So what that means is delta T over delta T. So delta big T is rate of change, change in temperature, and delta little t is time. So rate of change of temperature increase. Okay, so because of that, we are eventually going to have to calculate the percentage uncertainty in large T and the percentage uncertainty in T. However, before we do that, we know that delta T is actually T final minus T initial. So delta T itself is combined from two different values. So we have to firstly work out the total absolute uncertainty in delta T. Okay, because the TF and TI are both measured in degrees, we simply combine the uncertainties by adding the absolutes. So that means that the total absolute uncertainty in delta T is simply plus or minus 2 degrees C. Okay, and therefore what we now can do is use that to allow us to work out the percentage uncertainty in delta capital T. So if we then do that first, so the percentage uncertainty in delta T is our absolute divided by our actual value, which in this case is our 70 less our 19, and then we times that by 100. And when we do that, that comes out at 3.92%. So that's our percentage uncertainty in delta capital T. What we now have to do is work out our percentage uncertainty in delta small t. So same way, absolute divided by the actual value multiplied by 100, giving us a percentage uncertainty here of 0.4587%. So when we then add those two percentage uncertainties together, the total percentage uncertainty is at 4.38%. So we can now use that to work out our absolute in the final value for rate of temperature increase. So the best thing to now do is actually work out our value for delta T over delta T. So that is our 70 minus 19 divided by 218, which gives us 0.2339. Okay, we know that's correct because if we look at our 4 options, they're all that sort of value. And now finally, to calculate the absolute uncertainty, we work out 4.38% of 0.2339. So 0.2339 multiplied by 0.0438 gives us a value of 0.01. So that means that what we have here is our value for delta T over delta T is 0.23 plus or minus 0.01 degrees C per second, and therefore we can see that the correct answer here is option A. So now looking at equations of motion, what should the value for the student's acceleration be? So now we need to use an equation of motion. We're being asked for A, we've got U, we've got V, and we've got T. So the formula that combines all of those is V equals U plus AT, but we're after acceleration, so we rearrange that and we've simply got V minus U over T, which as you'll probably spot is exactly the formula we used to use at GCSE for acceleration anyway. Okay, so once again, to work out the total uncertainty in A, we'll have to work out the percentage uncertainty in change in velocity and the percentage uncertainty in time. But before doing that, we need to find the total absolute uncertainty in that value for V minus U. V and U, once again, are measured in the same units, and therefore the total uncertainty in delta V, i.e. V minus U, is simply plus or minus 0.02 meters per second. Okay, so that's our absolute uncertainty in V minus U. From there, we can do our percentage uncertainty in delta V. So our absolute, 0.02, divided by our actual value, so that 0.81 minus 0.19, 0.19 multiplied by 100, and that gives us a percentage uncertainty of 3.2258%. So that's our percentage uncertainty in delta V. We then work out our percentage uncertainty in T. So that is our absolute for T, 0.01, divided by our value for T, 1.82, times by 100, which gives us a value of 0.5495%. So therefore our total percentage uncertainty is the sum of those two, which is 3.775%. If we now actually calculate our value for A, so we've got our V, which was 0.81 minus our U, divided by T, which was 1.82, we get a value for A of 0.34 meters per second squared. And then our final step is work out 3.775% of 0.34. So we take 0.34 and we multiply it by 0.03775, which gives us a value of 0.013 meters per second squared. So our final value for A is 0.34 plus or minus 0.01 meters per second squared. And when we look at our options, that is option B. Okay, now the plot thickens here because once again you are looking at a fairly straightforward formula. You're looking at the formula for Hooke's law because we're being asked to find the extension. Okay, we've got a weight, which is a force, and we've got a value for the spring constant K. So we know that we're using F equals Kx. But the added bit here is that we've got springs connected in parallel. So not only do you need to be able to work out your uncertainties, you need to draw on what you know about what happens to spring constants when springs are in parallel. Now, when you put springs in parallel, their stiffness will increase. So what that means is that the total spring constant for springs in parallel, and in this case, will be the sum of each of the individual spring constants. Okay? So the first thing we need to do here is say, well, okay, what is our actual overall value for K and what is our overall absolute uncertainty for K? So K total, because the three springs are identical, is simply 275 plus 275 plus 275, which gives us a value of 825. Okay, and because the uncertainty in each value of K is plus or minus 3 newtons per metre, because we are summing three values for K, we can simply add together the three values for the uncertainty, giving us plus or minus 9 as our absolute uncertainty. So there is our new value for K, taking into account the fact that there are three springs in parallel. So once again, we now have to work out the percentage uncertainty in K and the percentage uncertainty in W, which is our force. So let's stick with K first of all, because that's what we've been working on. So our absolute was 9, our actual value was 825, and that gives us a percentage uncertainty in K of 1.09%. If we do the same now and work out the percentage uncertainty in W, which remember is our force, so we've got our absolute of 0.2 newtons divided by our actual value of 15.2 times by 100, and that gives us a value of 1.32% uncertainty in the value for W. So our total percentage uncertainty is the sum of those two. So when we add those two together, we get 2.406%. Now we actually have to work out the extension. So we take our formula for Hooke's law, F equals Kx, and we rearrange that to give us X is F divided by K. And when we plug our values in there, we have our force of 15.2 newtons divided by our value for K that we worked out of 825, which gives us a final value of 0.0184 meters, which of course is 1.84 centimetres. So the last thing we now need to do is to work out 2.406% of that 1.84 centimetres. So if we do that and we say, well, 1.84 multiplied by 0.02406 gives us a value of 0.044, and therefore our value for x is going to be 1.84 plus or minus 0.04 centimetres. And if we look at our answers, we can see that that wasn't one of the options that you were given. So this was another one of those ones where you can be forgiven for getting your answers incorrect. Okay, so this is one where I had to go to the source and ask them why they didn't have any of the correct solutions. Okay, but you can be confident that the answer is 1.84 plus or minus 0.04 centimetres. So apologies if those threw you off, because actually in this instance you weren't provided with the actual right answer. Question 4, once again, was another one where unfortunately you weren't actually given the right answer. So again, hopefully you'll be able to see how this works, and it may be that you did actually get this one right. But my apologies, as I say, these are from a different source, but hopefully once I've gone through it you will be able to follow. So once again we're looking for power. Okay, so we're looking for a final quantity using the two that we've been given. But again, we've got a fly in the ointment because we've got resistors in series to contend with first of all. So hopefully we remember that when we've got resistors in series, their total resistance is simply the sum of the individual ones. Okay, so in this case, what that means is our total resistance is 283 plus 145, giving us a value of 428. Okay, and because, as we've seen previously, these are both measured in ohms, we can simply sum their absolute uncertainties. So therefore, that is plus or minus 5 ohms. So there is our new value for resistance. Now, we're being asked to work out power, having been given resistance and current, and therefore the formula we're going to use in this instance is I squared R. So what we'll do first of all is let's actually calculate the value for power that we will be working with. So our current here is 566 milliamps, so that's times 10 to the minus 3 squared, multiplied by our value for resistance, which we just calculated to be 428. So our total value for power is 137.11 watts. Okay. So now to look at the uncertainties. Let's start with working out the percentage uncertainty in R. So percentage uncertainty in R is our absolute, which was R5, divided by our value, which was 428, times by 100, which then gives us a value of 1.168%. If we then do our percentage uncertainty in I, we take our absolute and divide it by our actual. Now remember, because these are both measured in milliamps, I can omit the times 10 to the minus 3 because the percentage uncertainty is a ratio, so we don't have to include the units, and therefore I can simply work in 3 and 566. So when you do that, you end up with a percentage uncertainty in I of 0.53%. However, if we go back to our formula, power is I squared multiplied by R. So the thing that we have to contend with here is that the percentage uncertainty of I is 0.53, but therefore the percentage uncertainty in I squared is going to be that 0.53 plus 0.53. So it's going to be 1.06%. Okay, because we've got two values for I, and therefore we sum their individual percentage uncertainties. So therefore our total percentage uncertainty, taking into consideration all of that, is that 1.06 plus 1.168, giving us 2.23% in total. So the last thing we now do is we work out 2.23% of our calculated value for power, which was 137.11 there above. So 137.11 multiplied by 0.0223 gives us 3.0576. So our value in this case for power is 137 plus or minus 3 watts. And as I mentioned at the beginning, unfortunately from the source you weren't given that as a correct option, so you can be forgiven if you didn't manage to get that one correct. And then on to number 5. So number 5 looks at a setup that you should be familiar with, trying to determine the internal resistance of a cell. So the internal resistance is given the symbol lowercase r. Okay, so you've been given a value for EMF, you've been given a value for V, sometimes referred to as V load, and you've been given a value for I. So the formula that you're going to need in this case is V is equal to EMF minus IR. Okay, and then if we rearrange that to make R the subject, what we end up with is minus R is equal to V minus E over I. Okay, now if you're not confident in how that rearrangement came about, pause it for a moment and just have a go at doing each step by yourself. But that's how we're going to use this value here. So let's start by actually working out that value for R. Okay, so we've got V minus E, so we've got 6.83 minus 9.10 all over our value for current of 471 times 10 to the minus 3, because it is milliamps. Okay, now when you work out that value for 6.83 minus 9.10, you'll get a value of minus 2.27. So what that means is that this minus R here will cancel, and when we then work it out, we end up with R coming out at 4.8195 ohms. So there is our value for R. Now we want to work out the uncertainty. So what we have to do first of all is work out the total absolute uncertainty in this change in PD, that is V minus EMF. Now they're both measured in volts, and therefore we can simply sum their absolute uncertainties. Okay, so the total absolute uncertainty in PD values, okay, so that's our V minus EMF, is the sum of the two of them, which is plus or minus 0.09 volts. From there, we can work out now our percentage uncertainty in, I'm going to call it PD still because it is V minus E. So that is our absolute, which is 0.09, divided by the calculated value for 6.83 minus 9.10, which, as I say, was minus 2.27. Now we can disregard the minus sign in this case because this is all about relative values for uncertainty. And then we multiply that by 100, and we end up with a percentage uncertainty of 3.96% in our value for V minus E. If we then do our percentage uncertainty in current, we take our absolute, we divide it by our actual, and remember once again we do not need to include the times 10 to the minus 3 because they're both measured in milliamps and this is a relative calculation. When we do that, we end up with 0.4246%. So that means that our total percentage uncertainty is the sum of those two, which is 4.38%. So the last step is to work out 4.38% of our value for R that we had up here of 4.8195. So we take 4.8195, multiply it by 0.0438, which gives us a value of 0.211. And then because it's important that we keep these values, these sig figs, exactly the same, that means that R is simply 4.8 plus or minus 0.2 ohms.